Hi, everyone. So we are moving into chapter 6, unit 6, which is vectors. So we're looking at 6.1 here, introduction to vectors. So we're switching from rates of change that we've been doing in calculus now to vectors. So just an example of what we would use something like this for. Oh, I'm just trying to move up here. Um, let's say you're in a boat, right? So the boat is in the water. The boat has an actual engine. So whether it's a small boat, whether it's like a cruise ship, um, and it's using its engine, it's using its motor to get to its destination. But we have other forces acting against us, right? So we have wind, right? That could be going with us or against us. And we also have waves. And so that might cause us, these forces might cause us to actually, when we're doing our calculations in the boats, the larger boats do that calculation for you now. We might need to change direction slightly to actually get us there sooner, so that we're not hitting, let's say, the waves head on, right? So that would be what a vector is the direction that we're going, but also the forces that are acting against us. So what is the difference between the key ideas here, a scalar and a vector? So a scalar is a quantity. So a scalar is a mathematical quantity that describes magnitude, basically, or size only. Magnitude or size, same thing, right? So basically length, with or without units, depending on if the question gives you the units or not. And it does not include direction, right? So when we talk about distance, distance is always positive. It's a measurement with no regard to direction. So for example, I say, if you walk out of your house and turn right and walk 1 kilometer, right? What's your distance away from home? 1 kilometer. If you just go with me here, if you walk out of your house and turn left and walk 1 kilometer, what is your distance away from your home is still 1 kilometer, right? So scalar does not include direction, whereas displacement that we were talking about before does include direction. And so if it has a positive or negative value, that tells us our direction from our original point. Okay, so something like speed is a scalar. Speed is, again, if I'm driving to Toronto and I'm driving 100 kilometers an hour on the highway, I'm driving home from Toronto to London, I'm driving 100 kilometers an hour on the highway, my speed is 100 kilometers an hour, I have no idea which direction I'm going in, right? So that would be a scalar. Whereas a vector would be like velocity that we talked about in the past. So a mathematical quantity that describes both the magnitude, which would be your length, and the direction. So this would be your distance, and this would be the direction that you're going in. It's also known as a directed line segment because you've got your line segment, your distance, but directed, kind of the direction is in there, right? And it can be represented in several ways. So let's say it's represented, just showing you here by words, by a diagram. Sorry, I just saw that that was off. I'm just going to say it's close enough. It's just when I open it up in Word, again, on the school computer, whereas here on my Mac, it just opens differently. And sorry, I didn't notice that, but it's not a big deal. So let's look at a vector by words, right? So again, a vector has to have two pieces of information given to you, both the magnitude, the length, and the direction that you're going in. So it can, in words, I can just say, I have a magnitude of 4 meters at an angle of 40 degrees to the horizontal or 40 degrees from the horizontal. So the word to or from could be interchangeable here. So there's my direction, right? 40 degrees. And there's my distance, my magnitude. And this box is associated with number 2. Okay, so that's it for words. Just the 4 meters would be my scalar, right? Would be my magnitude, but not direction, but because it has a direction, that turns it into a vector, okay? And it's usually given in angles. So moving it to number 2, by a diagram, so a geometric vector here. So it's the same wording as before, just turning it into a diagram. So they're kind of connected. So 4 meters here is my length, is my distance, and my direction at an angle of 40 degrees, again, to the horizontal or from the horizontal. There's my dotted horizontal line. So I'm coming from the horizontal up. I should have, it looks like an arrow there. I think it is, but it's just thrown off because the diagram moved. So I can kind of draw that in. Let me grab my pen here, right? So you put an arrow there indicating that that is 40 degrees in the direction that it's going in. And there's my magnitude, but I have to put a scale here. So first let's look at this box to talk about the direction of the vector. So point A here is the starting point, the initial point of the vector, but we actually call this the tail. So just to indicate here, that point is the tail, which is the starting point. Point B is the end of the vector, or the terminal point we learned in grade 11, right? And it's also known as the head. So it's the ending point or terminal point. So to me, it kind of seems backwards, right? Because the head seems like the beginning and the tail seems like the end to me. If it's not confusing to you, awesome. So one way I think about it is this is like a solid arrow at the end here, which to me looks more like a head, right? So like your head is larger than your feet, let's say. So then if I look at it and this is where the arrow is at the head, then I know that the opposite point is called the tail, but just know that your starting point is at the tail. And once you draw some of them and once we do some examples, you know, hopefully by like lesson 6.3, you would be, maybe even 6.2, you'll be used to that. So just kind of catch that and make sure that you're noting that. Anything else I want to point out here? So this is our vector line. We talked about point A and point B. I think that's probably, yeah, I think that's it. So let's move on to symbols. So this indicates, this line with the arrow here indicates a vector. So this is called vector AB when the endpoints are given. Or again, you might have a diagram where the endpoints are not given, and then you can just put any variable you want. We'll use V for vector here when no endpoints are given. So just a variable with the vector symbol on top indicates vector V or vector AB. And again, just to point out, it does go in order. So A is the tail, the way you have to draw it, tail first, and B is the head. And if I just had AB without the vector symbol on top, then that would just indicate a line segment, right? Like we've done in the past. So that would just be a line segment. So to know what's a vector, I have to have the symbol on top. That's basically it for that one. Okay, so again, we talked about magnitude. Magnitude is the length of the vector or the distance, let's say. And we indicate that with vector AB, so the symbol for vector AB, but basically with absolute value signs on either side. So those lines that you see means that you're indicating a magnitude, which is a distance. And that is a quantity, right? So the length of a vector, let's just write down that that's a quantity only. And it indicates, again, the length or size of a vector, or when the endpoints aren't given and I can't say it's AB, I could just say the magnitude of vector V, right? It's always a positive measure. So you always indicate the magnitude as positive. The angle that we get in the question is going to give us the direction. But so that's another way, like basically these look like absolute value signs. So absolute value signs make everything positive. So those are linked there to help you remember that. And again, distance is a positive measure. Again, going out of your house and turning right or left, both ways, you're 1 kilometer away from home, that distance is always positive. So now let's look at some terms here. If I have parallel vectors, what does that mean? So parallel vectors are vectors that have the same or opposite direction. So or here is important. They can go in the opposite direction, but not necessarily the same magnitude. So they don't have to have the same length. I'm just going to say they don't have the same length. They can. I just didn't want to write don't have to have. So they don't have the same length. They can, but they don't have to have the same length. So purposely here I've shown, if we look at, and again, when we are saying what these vectors are, we start with the tail to the head. So this would be called vector ST, as you see here, vector ST. This will be called vector Q to R. So starting with the tail and ending with the head. So vector QR. So I've purposely drawn them so that they don't look like they're the same length, right? Because it says here they don't have to be the same magnitude. So they can go in the same or opposite direction. So I can say that vector QR right here is parallel, right? Parallel to vector ST, which is exactly what's shown on the paper here. Or I can say that vector QR, back to QR in this direction, is parallel to vector TS. Well, TS means I have to start my tail at T and end it at S, right? So this is vector TS. So all I'm showing is that they can go in the same direction, right, and be parallel. They can go in the opposite direction and be parallel. They don't have to be the same length. They just literally have to be the same distance apart from each other all the way along the two lines given, okay? So whereas opposite vectors are different, opposite vectors have the same magnitude, they have the same length, but point in the opposite direction. So they're literally opposites of each other. So if they're opposites of each other, keep in mind that they do have to be the same length. So just indicate that they have to be the same magnitude. So just writing here, these two should look like they're the same length. And so that is on purpose. And they do have to be in opposite directions as well. Okay, so again, this indicates magnitude. The vertical lines on either side are the absolute value sign there. So the magnitude of vector EF, so tail to head, right, EF, is equal to the magnitude of vector G, starting with the tail, G to H. So this is just saying that they're equal, meaning equal in length. Okay, that's all that that's saying, is that they're equal in length. We're not saying that they're opposite yet. This one here is saying that vector EF, again, starting with E, the tail, to F, is equal to, this is the opposite of vector G to H. So this is saying that they're equal to each other, and this negative symbol is indicating that they are opposite to each other. So that's how you write opposite. Okay. So again, E to F, vector EF is parallel to vector HG. If I was to write parallel would mean that I would write them in the opposite direction here, right? Because I'm starting at H as the tail. This is not a tail, so H to G. But again, that would be parallel. They would not be opposites. That's why there's no negative symbol there. Or vector EF is parallel to vector starting with the tail G to H. So these two are parallel to each other. Vector EF to the brown one that I drew, HG, are parallel to each other, but I just want to erase that because the important thing to mention is that it's saying they're parallel, but that they're not opposite, right? This statement here, vector EF is equal to, in length, to the opposite of vector GH. These are opposite to each other with that negative symbol. And moving on to the last one, equivalent is maybe what you would think, kind of like exactly the same, right? So vectors that have the same length, the same magnitude, and the same direction as well. Everything is exactly the same, and they're also parallel to each other, right, in order to be equivalent, which it says here. So again, the magnitude of vector AB, starting with the tail important, A to B, is equal to the magnitude of vector, the arrow on top, C to D. So all that's saying is that they're equal to each other, magnitude to magnitude, length to length. This length is equal to this length. That's what that is saying. Vector AB is equal to vector CD. So if they're equal, then they're equivalent, we're saying, right? So if they're equivalent, this statement is also saying that they are going in the same direction, right? This is indicating that they're the same distance. This is indicating that they're going in the same direction, or else if they weren't, there'd be a negative sign, right? So therefore, vector AB is parallel to vector CD. So just all three things have to be true for them to be equivalent. Basically, you could take it and move it over and lay it right on top of the other one. And they would be the same length, same direction, and parallel to each other, meaning that they would end up on top of each other. Okay? So a vector's direction, if we're talking about the direction now, can be expressed in several ways. So there's two ways that we're going to talk about. for the direction, because here we're talking about the length, the magnitude. For the direction, how are we going to say what direction it's going in? So again, that boat that was in the water, how do we indicate what direction that it's going in? So one is called a true bearing, and we've seen both of these before, and the other is called a quadrant bearing. So just focusing on the true bearing. True bearing is a compass measurement where the angle is measured from north. I'm just going to make this red here. The angle is measured from north and it's going in a clockwise direction. It has to be clockwise. So we're always starting true north and we're always going in this clockwise direction. This is clockwise, right? So an example would be, I have a magnitude of length of 1.5 kilometers at a true bearing of 135 degrees. So if I know, if it says true bearing, or it even just says the word bearing, I'll talk about after, so I don't even have to have the word true there. But if it just said 1.5 kilometers at a bearing of 135 degrees, and that's all you have given to you is the degrees, you start north, and you know what direction you're going in, and just draw a vector that's 135 degrees away from north in that direction. So if I know from here to here, from north to east, is 90 degrees, and from east to south, right, would be 180 degrees. We're somewhere in this quadrant here between east and south. And so again, between 90 and 180, from 90 to 135 is exactly 45 degrees away, and half of 90-degree quadrant is 45 degrees. So we're talking about it like exactly the diagonal, not done it well, because I'm not using a ruler, but exactly the diagonal between them. Okay, so if I was to fill that in, I'm going to fix that here. If I was to fill that in with a straight line, let's see if I can do this well. So from here, yeah, not bad. And just trying to do a diagonal 45-degree line. Close enough. You do want to use a protractor. I also want to say when you're actually putting this on graph paper. So you probably do want to start practicing doing it as best as you can. But for now on paper, we can just do it as closely as we can. So then we want to indicate here that this is our direction. So we want to say that we're starting from north and all the way to this angle here is 135 degrees. And again, just to point out, this is the tail of the vector and this is the head of the vector. And we also should label, we've got our direction, but we don't have our magnitude or distance listed. So this is 1.5 kilometers, but have I driven, have I drawn, I'm trying to say, have I drawn a line that's 1.5 kilometers long? No, obviously not. So I need to put a scale here. So let's say that 1 centimeter is equal to 1 kilometer. Then if I'm drawing something that's 1.5 kilometers long, just indicating that this vector, right, would be 1.5 centimeters long. Be 1.5 centimeters long. And also have a ruler and try to draw it where it literally is 1.5 centimeters long. Because again, when we are moving into putting it on graph paper later on, it has to be precise when it's on graph paper. So when you have several vectors and you're calculating angles and calculating distances and things like that, when it's on graph paper, it needs to be exact, right? Just seeing anything else I'm missing. Oh, I am missing one thing. So I did mention that it doesn't have to say the word true. So it could just say a 1.5 kilometer at a bearing of 135 degrees, again, would mean a true bearing. And you'll see why when we look at the quadrant bearing, the difference. It's an obvious difference between them. Also to mention though, true bearings are always a 3-digit value. I always have to list it as a 3-digit value. What do I mean by that? So this was 135 degrees. Let's say if I was talking about something that was 10 degrees, I would have to list it as 010 degrees. If it was 9 degrees, right, I'd have to list it as 009 degrees. So just when it's a true bearing, it's always listed as a 3-digit value. In comparison to quadrant bearing, I don't have to do that. If it was something that was 30 degrees, I can list it as 30 degrees. If it was something that was 9 degrees, I can list it as 9 degrees. So it can be 1 or 2 or 3 digit numbers, okay? So quadrant bearing is a compass measurement also, but it is and has to be actually between 0 and 90 degrees west or east of the north-south axis. So I'm between 0 and 90 degrees. And what that means is I'm either starting north and I'm moving in this direction or this direction, meaning again, west or east or west, east or west. So again, this is east. It says the word we, right? Just in case, to make sure you don't mess that up. Or I'm just saying, I can start from the southern direction and move again east or west. So all it's saying is that I'm moving in an east or west direction, again, from the north or the south axis. So let's say I have something that looks like this. That's saying I have a 10 kilometer per hour vector at a quadrant bearing of north 30 degrees west. So the north 30 degrees west, hopefully you would see, is our direction, right? So this would be our magnitude or length. Well, in order to draw our length, I first need to know where I'm drawing it. I need to look at the direction first. So again, I'm starting at north, right? And I'm moving west. So be careful here. North to west means I'm kind of moving in a left direction, 30 degrees. So again, if you kind of look at, I can erase this after, but just kind of in your head, I'm saying, you kind of look roughly at where 45 degrees is. And again, I'm not doing well at this, 45 degrees. And so 30 degrees from north to west, I'm not going 45 degrees, I'm going less. So you would just draw, roughly 30 degrees there. And again, really what you should be doing is getting out a protractor and measuring 30 degrees if you can, just to get practice, because you will have to do that later. So whether you do that now or not, just know that you're going to be doing that later. And then you have to indicate what direction you're going in. So I'm starting north and I'm moving west, and indicate your direction as 30 degrees. But then we also have to list this 10 kilometer per hour. So I can list that here, 10 kilometers per hour, but I need to put a scale because obviously that's not 10 kilometers per hour. So let's look at a scale here. Scale can be whatever we want to make it, right? It doesn't have to be the same as what I say it is either. Just have it be reasonable. So if I made 1 centimeter, I'm going to erase this, so don't write this down. If I made 1 centimeter, 1 kilometer, and this was 10 kilometers, then I'd have to have this be 10 centimeters. That seems a little long, right? So in that case, like the scale we had before, that doesn't make sense here. So let's say I had 1 centimeter then. What if it equaled 5 kilometers per hour? Then if this is 10 kilometers per hour, then my vector would be 2 centimeters long, right? So this vector, I would get a ruler and draw it 2 centimeters long. I can get a protractor and get it exactly at 30 degrees. And that would be, so the main thing is if you see these compass directions, northwest, northeast, south to west, or south to east, it's always going to start with a north or a south, and it's always going to end with a west or an east, which is what this is saying here, right? Then you know you've got compass bearing. You know that your answer is going to be between 0 and 90 degrees. If it doesn't show these compass directions, then it's a true bearing, and it's either one or the other, and that's it, right? So now let's take a look at some further examples here, just to make sure we're understanding what I was talking about at the beginning of the video. Whether something is a scalar or a vector is kind of a good starting point, right? So again, a scalar is a quantity. It talks about the length, the magnitude, but not the direction. A vector talks about both. So just take a look at these. And is it telling us one piece of information or 2 pieces of information, right? A vector is something that's giving us both the length, the magnitude, and the direction. Okay, so let's take a look here. I have a temperature of 25 degrees Celsius. So 25 degrees Celsius would be the temperature, but I don't have a direction, right? There's no direction given to me. There's only one piece of information given to me, so this would be a scalar. What if I'm driving 80 kilometers per hour? Well, we did talk about speed before, right? All that says is speed. Where is speed listed? So speed is listed as a scalar, right? Not a vector. Because again, I'm driving 80 kilometers an hour to Toronto. I'm driving 80 kilometers, just as an example, back to London. It doesn't give me the direction. I have a force. I'm just going to read it first and then go back. I have a force of 8, that's newtons, downwards. So from science class, right? So your force is gravity. Gravity forcing down on an object, right? So you have both listed. You've got your magnitude, your, let's say, distance or length can also be used as a force, so that would be the number 8, and your direction then would be downwards. So you're assuming like straight downwards, like south. So because you have both listed, then this would be a vector. Okay, what do you think about this for a second here? I've got a mass of 22 kilograms. So a weight of 22 kilograms. So this mass could be anywhere here. This mass could be your mass on Earth, your mass on another planet, wherever you are, the mass is the same and the mass is 22 kilograms. So we're only dealing with one piece of information here, which is weight. So that is a scalar. Okay, what if I'm flying 7 kilometers above the ground? I want you to think this through. I've got my 7 kilometers, so I have my length or my magnitude, right? And then you probably are thinking, okay, I've got above the ground as my direction. But I just want you to slow down there. The way that I'm drawing it with my degrees and everything that we have just above here, would I be able to draw it? Do I know that I'm flying 7 kilometers again with an amount given to me, like at a direction of 80 degrees from the horizontal, 130 degrees from the horizontal? I don't know where I am above the ground exactly, even though it sounds like I'm given a direction. So this is still a scalar. So just be careful with that, to think that through. Think if I was to draw it, maybe it might help you. If I'm running 15 meters per second east, is east a direction? If it's exactly, true east, you're going exactly in this direction, right? And you're running at 15 meters per second is your magnitude or length, then I'm given both. That's totally fine. That would be a vector. Okay. This one is somewhat similar to the mass of 22 kilometers to think of. I have the weight on a bathroom scale. It's not telling me what the weight is. This is giving me a direct mass of 22 kilograms, and that mass would be anywhere that I am. This is slightly different because if I'm looking at how much I'm weighing or how much something is weighing on a bathroom scale, that will change depending on where you are, right? Gravity affects a person's weight. So your gravity on Earth compared to your gravity on another planet will change. So that's giving you another value. So it's different in different places. So because gravity is different in different places, this is actually a vector. Okay, so now we've practiced basically the first page. No, we're just going to start the first page here with number 2, describing each vector in words. So we're going to look at, on the first page was number 1 in words, and then we're going to move on and again practice drawing these vectors afterwards. So describe each vector in words. So I notice here, again, sorry, this arrowhead here is just thrown off because the word's opening and it should just be here. So you can erase that there. And again, hopefully if you've printed this out, you don't have this issue then, right? But there's no degrees listed either. I don't know where that dropped off to. So let's just list it as it should be 130 degrees. So that's part of the original diagram. It's just missing, okay? So because again, if it's a vector, it has to have my magnitude, my length of 15 kilometers, there we go. And it has to have my direction, which is 130 degrees. This would be from the horizontal. So now we're getting it into words now that I'm saying it out loud, right? The vector is drawn 130 degrees from or to the horizontal. Again, those words can be interchangeable. I like from personally because it's kind of telling you that's your starting point. The magnitude is 15 kilometers. So let's say I would write that out as 15 kilometers at an angle of 130 degrees. Again, I like from the horizontal. You can put to the horizontal, not going to be wrong. From, again, I know I can't say one thing and be writing something else at the same time, right? 15 kilometers at an angle of 130 degrees from the horizontal. So that is like example number 1 in words. Move on to another one. So this would be a true north bearing, right? We're starting north, a true bearing, and we're moving clockwise. And so we have that listed as 310 degrees. And again, that doesn't make sense, right? Because 9, 90, 180, 18, 9, 18, 27, 270. This is supposed to be going right to the line. It's just thrown off the arrow because of the Word document again, okay? So we have our direction and we have our magnitude. So it is a vector. This is the tail of the vector. This is the head of the vector. This is the starting point to draw it. And it usually starts at the origin, right? And then that's the ending point of the vector. So I could write that out as, it's usually if you saw a magnitude first, right? Your magnitude listed and then your direction next. So your distance first. So I have a distance of 12 meters per second at a true bearing. We talked about how we know that, starting north and going clockwise, at a true bearing of 310 degrees. And I'm also just going to write here, just to show, I could also say I have a 12 meters per second at a bearing of 310 degrees. I don't have to write the word true, right? Or put that in brackets, right? Optional, of 310 degrees. Okay, this one's thrown off as well. So again, if you've printed this out, it should only be going, starting at north, right? And stopping at the vector, that's where your arrow should be, is 60 degrees. And this 12 meters per second is again the length of the vector, just closer to the line. It's not on the horizontal is what I'm saying. So right away, hopefully you notice that I'm not going clockwise. Well, if I'm not going clockwise, that's a pretty clear indicator that it has to be the other one, right? Quadrant bearing then. So I've got my, again, you have your magnitude first. So I'm going at a length of 12 meters per second at a quadrant bearing of, and then slow down here, at a quadrant bearing of, you have to start with north or south. So I'm going north, then you put your degrees, 60 degrees, and you were in what direction, remember? West or east. So this is going west. If you need to label it, go ahead. Label whatever you need to, as long as you're not getting something wrong, right? The more information, the better then. So I'm at 12 meters per second at a quadrant bearing of north, 60 degrees west. And I'm also going to put here that you don't necessarily have to write out all of this, or you might not see all of this written out. It might just say 12 meters per second at north, 60 degrees west. And all this in the brackets could be missing. So again, just to say, or just to write down, 12 meters per second at north, 60 degrees west. And that would be enough for you to know that it was quadrant bearing because you've got the 2 compass directions there. And there's your magnitude. That's all you need. So this is just very simplistic. So again, to me, having the more information there is better, but if it gives it to you in this notation, make sure that you understand that would be quadrant bearing. And that's still all you would need to write. Okay, so moving on to number 3. Drawing now, like we said, comparing it to, still on the first page, let's say number 2, drawing the vectors. Let me see if anything is thrown off here. Yeah, a little bit. Draw a geometric vector with each bearing that's given to you, right? Show the scale that you used on each diagram, because obviously, so here we have a vector V and it's equal to 10 kilometers. So what I mean by the scale is I'm obviously not drawing something that's 10 kilometers long. So to start, I have to think of my scale, and I'm at a bearing of 150 degrees. So again, this has nothing to do with this question. I wish I could erase that, but I can't. That is to do with the other question. So I'm just going to erase this here. And so this B is vector U at 100 kilometers per hour at a quadrant bearing of, again, south 20 degrees east, just to separate those to make sure that that is not part of this question at all. So I have to label it as vector V. I don't have any variables given to me. I know that it's 10 kilometers, so I could start with a scale because I've already kind of played around with something 10 kilometers in length. If I had, again, 1 centimeter equaling 5 kilometers, then if I want 10 kilometers, then my vector is going to be 2 centimeters long in length, right? And again, maybe the reason why I don't say 1 centimeter is 10 kilometers, and that way I only do a 1 centimeter vector, is you see how I have to write numbers around it and the direction of the degrees. It's a little squished. So if I can spread it out a bit, a reasonable amount, right? Stretch it out a little bit. Don't make it as physically small as you can. Have some room there. So vector V is 10 kilometers, so I know I'm drawing something that's 2 centimeters long, but I have a bearing of 150. There's no compass directions around here, so I know that it's a true bearing, right? So I know that I have to start from the north, and I know I'm going clockwise. So this would be 90 degrees, this is 180 degrees. Again, what would the diagonal between these, between east and south is 45. Right? So what's 90 plus 45? 135, and this is 150, so I'm going beyond it. So that just helps you with how to draw it. So I will just, again, you're just kind of eyeballing that in your head, the halfway point, just to tell you that I'm going beyond the halfway point. So there we go. And again, I should use a ruler, and that would be 2 centimeters long. But I'm going to indicate that that is, well, here, let's finish it first. And I do my compass direction here, and I write in that that's 150 degrees, and I add that in. I've got my scale. I know that my vector is 2 centimeters long. I've got my 150, so now I just need to put my magnitude. So I need to say here that the vector V is equal to 10 kilometers. Be careful, no per hour there, just 10 kilometers. And that's it. So moving on to B, vector U is 100 kilometers now per hour at a quadrant bearing. Well, they made this easy because they told us it was a quadrant bearing of south 20 degrees east. So again, when it's quadrant bearing, it's either going to start with north or south. So here's our south. Again, here's our west and east. We know that we're going in the direction of east. So starting south, moving east, and only 20 degrees. If I was going halfway between them, that would be 45. So it's almost like a quarter of the way, if you will. And again, you can get a protractor and do exactly 20 degrees, or you can just eyeball it, but know that you will need to know how to do that when we're graphing. So then indicate that you're starting south and ending east, drawing your 20 degrees there. So there's my 20 degrees. And then I also need to say that vector U for the length is 100 kilometers per hour. Vector U is 100 kilometers per hour. What am I missing? I know it's quadrant bearing. I've got my vector length. I've got my my degrees, my direction, but I have to have a scale, right? This isn't 100 kilometers long. So we always, in centimeters. So 1 centimeter is equal to, again, I feel like if it was equal to 100 kilometers, 1 centimeter is a little short. So if I made it equal to 50 kilometers per hour to fit everything in, then my vector is going to be 2 centimeters long, right? 50, 50, 100. Okay, let's move on to number 4. And then we're almost done here. Write a true bearing. Now notice how it's 3 degrees there, right? The true bearing has to be 0, 3, 0 of 30 degrees as a quadrant bearing. So we're switching from one to another. So I know how to draw something that is 30 degrees from north, going in a clockwise direction. I know that halfway through is 45 degrees, so I'm going not quite 45 degrees. So clockwise, there's my 30 degrees. And if I was writing that as a quadrant bearing, again, there's my south, there's all my compass directions. So I'm just starting at north, 30 degrees towards east. And that's literally it. So 0, 3, 0, 30 degrees is true bearing, I'm just saying, and switching it over, this is quadrant bearing. I'm just saying that for short. So north, 30 degrees east. To me, not too bad, right? So number 5 here, the opposite. We're going to start out with a quadrant bearing, write the quadrant bearing south 75 degrees west, and then switch it up to be a true bearing. So just keep in mind here that we need 3 digits right away for true bearing. So I'm going to go ahead and really all I care about is the numerical, but I'm going to obviously graph it to help me out. So if I'm starting south and I'm headed west, so south and 75 degrees is almost 90 degrees. It's definitely past 45. So again, maybe something like that. Let's get rid of that. West. Let's try that again. There we go. Not too bad. So starting south, headed west, 75 degrees written in there, right? But if it was a true bearing, I would be starting with north and going clockwise. So I'd be starting north and I'd be going all the way around to here. And I need to figure out what that full angle is. Well, I know that that's 90, another 90, or a straight line here is 180. So I have 180, and then see how it's 180 plus 75 degrees? The 180 plus from south to west, I also headed another 75 degrees. So if I just add those up on my calculator or in my head, I have 255 degrees. So I would just write that as a true bearing. So this is again quadrant bearing, south 75 degrees west is equal to 255 degrees true bearing. That's all you'd have to write is 255 degrees. Okay, so number 5, switching it up a little bit here for 5 and 6. Back to the second page. So we're talking about parallel vectors, opposite vectors, equivalent vectors, and getting practice with how to write those. So name all equivalent vectors, parallel vectors, and opposite vectors that are true in the following, using the following diagram. So if we go with equivalent vector, oops, my pen, equivalent vectors first. Equivalent vectors meaning that they are the same length exactly and the same direction. So again, they are literally the exact same thing. You would take one vector and if you moved it, it would lay on top of the other vector. But keep in mind that it's also going in the same direction. So I've got vector EF here. I can see this one's the longest one, this one's the shortest one, meaning there's nothing that length in terms of that long or that short. So that means I don't have anything equivalent to vector CD, again, tail to head, to or a vector AB, but I've got these 3 that I'm hoping to you guys, or if you were to actually measure them, all 3 of these are equivalent in magnitude and length, but they're going in different directions. So equivalent is same direction. So I've got the vector EF is exactly equivalent to the vector RS there. So to write that out, vector EF, again, tail to head, I have to write it out, is equivalent to, right, vector RS. And just to write that in, that they're equivalent. All right, so let's change our color. And obviously I'm gonna have other colors here. Actually, I'll see if I can leave it. Hopefully that doesn't confuse you. So in terms of parallel, let's do that in pink. Parallel vectors, the only thing is literally that they're parallel, right? They can go in the same or the opposite direction. They can be different lengths. They're just literally looking parallel. So you can see AB doesn't look like it's parallel to anything, but CD and EF look parallel. It doesn't have to be the same length and they don't have to go in the same direction. So also like H, right, tail to head, HG, right, and RS are parallel to each other, right? They're not going in the same direction, but that can still be called parallel. So I have a lot here that are parallel to each other. So I can say that my parallel vectors is vector EF, right, is parallel to RS, but that's also parallel to HG, be careful, tail to head, which is also parallel to vector CD. They're all 4 parallel to each other, just showing that the direction doesn't matter and the length doesn't matter. So again, just CD there, and I'm going to go on purpose a different length in an opposite direction. But those are parallel to each. So are the others, but just to point out those two for the definition. And now opposite vectors do have to have things that are the same about them, right? So opposite vectors have the same length, but they don't have to go, but they're obviously in opposite directions, which is why they're called opposite. So they are exactly the same length though, but opposite directions. So which ones do we think look like they're the same length? I think there's only one set there, right? And parallel to each other. So AB is not parallel to anything here, right? So the same length we said are these three. EF and RS are going in the same direction, so they're not opposite. So we have EF here, vector EF. Oops, I should have made that longer. Vector EF is opposite to vector, let's say HG. And so in order to say that, I put HG vector, but to say opposite, I put the negative in front, right? And I don't know if you noticed that there is another one there, right? These are the same length, opposite direction. These are the same length in opposite direction. So I also have vector RS, which is equal to vector, again, HG, opposite. Equal in length, but opposite direction, so the negative. And I can't say that EF and RS are opposite because they're going in the same direction, right? So moving on to number 6. Last one. The diagram below is a rhombus. Name all the equivalent vectors here only. So equivalent is exactly, right? So equivalent would mean exactly the same length, but also exactly the same direction. So equivalent, we want to just maybe say here, same length and same direction. Okay, so we already know what a rhombus is. A rhombus is like a square that's been pushed over, right? So again, all 4 sides with these ticks are equal in length, but that this, let's say, left side is parallel to the right side with these 2 arrows here, and this single arrow and single arrow means that the top horizontal is parallel to the bottom horizontal. So it could also, a rhombus is a special type of parallelogram, right? So if I was to say here, if I'm looking at a vector, there's no vectors drawn in, I have to draw in the vectors. So the same length, all 4 are the same length, but we have to talk about only the ones that are going in the same direction can be equivalent. So let's say I have this vector that I draw in, not good at doing a straight line. I will try again. So going in this direction, hopefully you can see the brown there. Putting the arrow tells me what direction I'm going in, right? So this would be vector AB. I know that it's equivalent in length, if you see here, to vector. It has to be the same direction, so I have to call it tail to head, DC. So those are the same length, but also going in the same direction. So those are equivalent to each other. That's one set. But also here I have to say, well, what if I drew my vectors in the different direction? Same thing, but different direction. What if I drew it this way? B to A, tail to head, and C to D, tail to head. Those vectors are going in the same direction and they're the same length. So also here we have vector B to A, because that is a different vector, is also equivalent to vector C to D. So if we're good with that, let's change it up and look at another one. We have also this vector here, starting with the tail, we'd call D to A, is going in the same direction as this vector here, right? C to D. So the second way here is vector, again, be careful that it's D to A, tail to head, is equivalent to vector C to B. And just to double check that, same length, we know they're the same length. We've got the ticks there, and same direction. but we could also switch that up and go the opposite direction. So we need to write that one out as well. So if I was to start with tail as A, going to D, and tail as B, going to C, so A to D vector is equivalent to B to C vector. And that should be all that you see that are going in the same length and the same direction.